Okay, so the reverse process uses the same number, but we're going to get that energy release. So if I bring these two nitrogens together and form a triple bond, I'm going to release 941 kilojoules. So I just flipped the sign. So I'm going to rewrite this. Now I have my two nitrogens, they're separate. I bring them together, excuse me, and I'm going to get negative 941 kilojoules per mole. Questions on what we do with that? Okay, and so then what that means is we're just going to add our products and reactants together, add the energies of our products and reactants together for bonds formed and bonds broken, but we are going to adjust our signs accordingly. Okay, that's what we need to do. If we are breaking the bonds, we need to make that sign positive. If we are making the bonds, we need to make the sign negative. All right, and so then to take it and do the example we did the other day, we had oxygen. We had oxygen plus 2 hydrogen went to make 2 waters, right? And so if I was to draw that doing our Lewis dot structures, we would have oxygen like that, plus 2 hydrogens, so a hydrogen and a hydrogen, a diatomic hydrogen, and then we're going to make 2 waters out of that. The waters look like this. I'm going to actually draw them in their bent shape. We're going to talk more about shapes today again. Shapes are super important, okay? So we have that. And so what I've got here is if I want to figure out the change in enthalpy for this reaction, it's going to be equal to 4 times, I'm still going to do my products before I do my reactants, just because it really does happen all the time. So 4 times whatever an OH bond is worth. Okay, but I'm going to write down broken. So negative. All right, and then it's not a charge. Broken, so negative, plus 2 times whatever an HH is worth. I'm sorry, this is formed, so negative. Okay, these are broken, so positive. All right, plus 1 times whatever an OO bond is worth. And then I'm going to make sure to have my negative signs and my positive signs in the right places. So I'm going to go up here. All right, you guys hold whatever the OH bond is worth in your head. You guys hold whatever the HH bonds are worth in your head. And I'll hold whatever we had OH8, I need the OO. I'm going to hold 498 in my head, okay? All right, so this is 498 kilojoules per mole times 1, and it's positive because they're broken. HH's, anybody remember what it was? 436? Okay, so we've got plus 2 times 436, you said? Kilojoules per mole. And then OH's, anybody remember that? 460. So it's going to be 460 kilojoules per mole times 4, and then we make it negative because they're broken. Okay, you could have made it 4 times negative. Actually, let's do it like that because it's actually 4 times a negative energy released, right? And then over here, it's a positive and a positive. And then we can put that in our calculator. And this time, we should get a negative number. If all is right with the world. And looking at them right now, it looks like all is right with the world. And I get negative 470. Okay. So I get our enthalpy here, how much heat is given off is 470 kilojoules per mole. Is that what other people got? Yeah, good. Okay. And now I'm happy because what happened here, this is what launched the space shuttle. This is one of the reactions that launched the space shuttle. And you see all that fire coming out of the back of the space shuttle. You know heat is being given off, right? So you do those mental checks on whether you've set things up correctly or whether you've taught something incorrectly. Yes?
How did you get the 4, 2, and 1, like before the OH bond?
Good question. How did I get those numbers I put in front? If we look at the 4 here, this is for the OH bonds in the waters, and there are 1, 2, 3, 4 OH bonds. Okay, in terms of the 2, there are 2 hydrogen bonds, or HH bonds. They're not hydrogen bonds, but 2 HH bonds, and there is one OO double bond. Okay, other questions? Yes.
How do you say would we get the bonds, or would we get like a word problem type question?
Oh, for this?
Yeah.
I'd give you the reaction like this. And if I gave you the reaction like that, so as a professor, you're trying to test one concept at a time, right? Not generally be looking at, occasionally you'll be looking at how can you put it all together, and do I care about all the concepts together? But if I gave you this, I might ask you to draw me all the Lewis dot structures first, and then I would ask you to calculate the energies using your Lewis dot structures. And what that would allow me to do, if I did it like that, that would allow me to, I could evaluate whether you can do Lewis dot structures, right? But then I can take your Lewis dot structures and evaluate whether you've done this correctly. Does that make sense? But so it might be a word problem, but it would be this reaction. You would get the reaction. I wouldn't write that out in words. I wouldn't write oxygen combines with hydrogen to make. And we haven't learned to balance equations yet in this class, right? We haven't learned to balance equations, so I would have to give you a balanced equation. Other questions? Good question. Yes.
Will we have that table on our exam?
Yes, you don't need to memorize any of those numbers. You'll have the table you need. You'll have all constants you need. I will give you all formulas you need. I don't know if we have any equations. We probably have some equations. We did light this test, right? So I'll give you all the equations you need, and then I'll maybe give you a couple extra equations more than you need, right? They'll probably be all equations we've worked with. Other questions? Okay, let's go on and talk more about shapes then. So we were talking about shapes last lecture. This is still small, but I'm going to expand it. But I've got a table here. This is not the table from your book in terms of this, but your book has a similar table. I'm going to have to cross off a couple things on this table. The problem with the table in the book is it is really vertical, so it's just a mess in terms of how long it is. So I'm going to give it this table, but you have the same sort of things in your book. So what I want to introduce are in terms is more specific terms in talking about shapes. We can talk about atomic geometries or molecular geometries, and we can talk about electronic geometries. All right, so here it's talking about basic electron. They're calling this basic geometry here. Your book is going to call that electronic geometry. And what that electronic geometry is it's how many things are around your center atom. So here your electronic geometry is I have 3 things around my center atom, and so the electronic geometry is trigonal planar. And that might actually be my molecular geometry as well, because if those are 3 atoms, that's what the shape of the molecule is going to look like. But if one of those things is a lone pair, now you get a bent. Does that make sense? Okay, and what I'm going to do is I'm going to cross off this angular. I'm not sure where that came from. I have never, ever been taught or seen in a book to call it angular. But wherever this came from off the internet, apparently they have it, they don't call it angular as well. Bent. Okay. All right, so let's go ahead and we're going to review through some of these real quick. We've done most of these, but what we have here is, so we have, remember, if you have 2 things, they're going to get as far away from each other as possible, and that's linear. All right, we don't actually have, in regards to this geometry, if we have 2 things, if you had, you don't really ever do, you don't exactly do geometries where if one of these was a lone pair, right, it would still be linear, right? You have two atoms. In fact, if you have 2 atoms, it can't be anything but linear. Down here, we had our shape where we have 3 things around. If those 3 things are atoms, we call it trigonal planar. And because they're 3 things as far away from each other as possible, the angle between these things, or between the atoms, is going to be 120 degrees. Does that make sense? Up here, 180 degrees. I care about the angles, okay, as well. So here, if we take one of those groups and we replace it with a lone pair, remember we figured this out from the Lewis dot structures, replace it with a lone pair, then I end up with, I've got 3 things there in a bent conformation, but where there are well, I have 2 things around a center atom. If I have 3 things around the center atom and one of them is the lone pair, that's 120 degrees. When we get to tetrahedral, we'll have a bent that has a different angle to it. Okay. Questions so far on these shapes? And we did these shapes with examples last lecture. When we get down to where we have 5 things and 6 things around that center atom, I'm going to review that again because that was at the end of lecture last time, and we ran through 5 pretty quick and we ran through 6 even quicker. Okay. But go back and look at the last lecture and the last notes there. All right, so let's go ahead and look at, we have 4 things. If you put 4 things around a center atom, so here they're showing it with this wedge notation. This one is coming out at us, and that one is going back into the board, okay, or back into the screen. If you have 4 things, that's tetrahedral is your base shape, or your electronic geometry, your electronic geometry. And so arranging those in 3-dimensional space gives you a tetrahedron, and your angle is 109 degrees. And we call that tetrahedral. Okay. If we take one of those away and replace it with a lone pair, and our example was ammonia for this, we end up with what's called a trigonal pyramid, which is a little bit harder to see right here. If they maybe should have had that down a little bit, but that's a trigonal pyramid. All right. And then if we have 2 lone pairs, like water does, right? Water, oxygen, hydrogen, hydrogen, we're going to end up with a 109-degree angle for that type of bent because the base shape it's coming from is tetrahedral. Does that make sense? And once again, I don't want you to use this angular. Questions? Yes.
So do we need to know the angle?
Yes, you need to know the angles. So you're going to want to memorize the angles as you go down. It's going to be 180, 120, right? 180 for linear, 120 for trigonal planar, 109 here, and then you're going to have for when you have 5, your angles are going to be, you have a 90-degree angle. So what we have is we have a trigonal planar here, and then we have sticking up out above it and below it, we have 2 groups straight up perpendicular. So we've got 120-degree angles here, and then we have 90-degree angles here. That makes sense? Okay. So if you remember kind of the shapes, it'll be easier to memorize these. All right, so trigonal bipyramidal. So we talked about this before. An example of trigonal bipyramidal. Let's go through. We'll go through all of them, and then we'll do examples of all of them. Okay. So trigonal bipyramidal here, we've got so when I have 5 groups all around, I'm going to end up, that's what we call trigonal bipyramidal. So there's a pyramid up here, there's a pyramid down here. If you look at last lecture, I had models actually that we modeled for that. We had like 3D models we were looking at. Your book also will have excellent pictures at least, and it may have models you can turn around. Has anybody looked at it? Your book has some good animations at times. Anybody looked at it? Does it have models you can turn around? I'll email you when I email you the homework for Wednesday, and there will be homework this time. I'll find that website I had that had the models you could turn around on. If we take one of these away and we make it a lone pair, now we have what we call a seesaw. If you turn this thing on its side, do you see it could stand on these two and it could seesaw back and forth? That's where the name comes from. If we take 2 of those atoms away and replace them with lone pairs, then we're going to end up with what's called a T shape. Once again, we need to turn this one on its side to get it to be the T shape. All right, but what's going on? You notice that we put our lone pairs in the plane of the trigonal plane here first, because when you put them there, they have more space. There's more space there in that triangle because you have 120-degree angles. As opposed to if you put one of them up here, it would have to interact with, let's do it over here. If I was to put my lone pair here, I'd have a 90-degree angle, a 90-degree angle, a 90-degree angle, and that lone pair would be bumping into atoms more than it does if I put it in the plane of the triangle. Does that make sense? It's all about trying to give everything as much space as possible, and it's about taking the bigger things. Lone pairs are bigger than atoms in terms of the amount of electrons, or we can think about bonds. Lone pairs are bigger than bonds, the amount of space they take up. So that's our T shape, and then we can end up with a linear here. If we have 3 lone pairs, what can happen is that we end up with linear. All our lone pairs go out here where they have the most space, and then we end up with things straight across from each other. Questions on those? Okay, let's go ahead and look at some examples of those, since we did not cover these as carefully last lecture. All right, so we're going to do electronic geometries with 5 things around the center atom. And I've got the table here because you could use the table and just decide you're going to memorize the table. That'd be okay. There aren't more of these, okay? It is kind of a lot to memorize. In college, what I did was I just kind of learned the shapes, what made sense, where the electrons went. All right, so the base shape here is trigonal bipyramidal. Let's see, we do a BI, right? Yes. All right, your base shape is a trigonal bipyramidal, and so an example of this would be if we were to look at PF5. Okay, and I'm just going to draw out these Lewis dot structures kind of rapid fast, but essentially we're going to have our plane, right, where we in the middle, and then we're going to go. So what they do probably is they did this and this maybe. Put my fluorines around it. Actually, Lewis dot structure does not have to show shape. Okay, when you draw these, I'm kind of showing shape here. Does not have to show shape. Okay, and I'm going to draw these pretty quickly. I'm actually, since I know the shape, I know what the Lewis dot structure has to look like. All right, so that's what part of why I'm drawing them so quickly. I don't actually have these, not this far, I don't have these memorized. I have a bunch of the biological ones memorized. But that's an example, and so this is trigonal bipyramidal. Let's go ahead and see if I can find, I did not remember to look for that website this morning. Let's see if I can find it quickly. We're going to do Vesper shapes animation, I guess. And I'm going to hope that whatever this ChemTube thing is, there we go, it is that. All right, so this ChemTube, so let's look. Do we have a PF5? We even have PF5 here. Okay, and so trigonal bipyramidal, here they show you with this, I've got a triangle pyramid on top, a triangle pyramid on bottom. And I know we kind of went over this in fairly good detail, but these are the most complicated, so I think it's worth going over again. All right, so now what we need is we're going to replace one of those with a pair of electrons. All right, so an example of that, I think, is a sulfur. Yep, an S. So if we do SF4, like that, that is going to look like this. I'm going to have a pair of electrons there. And then if I draw it in its shape, which remember, you don't have to draw it in its shape for the Lewis dot structure, but you're going to use the Lewis dot structure to find the shape. Okay? And you see if you turn that on its side, it looks like a seesaw. Questions on that one? Okay. So let's go to that Chem 3D thing and see if they have a seesaw. It may not be the same one. Yeah, it is the same one. Here it is. So you see this one? So it's like a seesaw. If we turn it, let's see if I can manage to turn it right. Okay, there we go. So imagine it's sitting on these. We could, if I could grab it correctly, we could seesaw it back and forth. Imagine it seesawing. I'm clearly not going to get this. Okay, questions? All right. We have another one we could do. These are really weird. I could do chlorine tetra or pentafluoride, or sorry, trifluoride actually. So I could do chlorine trifluoride. What? Chlorine's going to be my center atom there. Why is that? It's not farthest to the left, so what rule might we use? I mean, it's the actual rule, not the farthest to the left rule. Do you guys remember that electronegativity, how much the atom wants electrons, increases as I go this way, but it also increases as I go this way? So chlorine is less electronegative than fluorine, and so it's more willing to share electrons. It's not happy about it, because it's pretty electronegative as well, but it's more willing to do so. So we would put chlorine in the middle, and I'm going to put 3 fluorines around it. Okay. And I know what shape I'm doing, which is a shape that requires 2 lone pairs to make it, right? To make it T-shaped. And so it's going to look like this. But if you were doing, if you got this on the test, you'd have to draw the Lewis dot structure using the rules we've talked about, right? And we can review those and do a ton of those on Wednesday. If we have time at the end of the day, we'll do some as well. You see how that's T-shaped? Okay. And then if we go over to our chem thing here, let's look for something that's T-shaped. Here we go. Maybe this isn't going to help us. Dipoles and here it is. That's not right. There we go. So this is going to show us T-shaped. It's not showing us the electrons, right? We've got a pair of electrons, one going back here and one going here. Okay. And then finally, for this set, remember, we're still doing 5 things around an atom here for our electronic geometry. We're going to have a xenon difluoride. And the xenon is going to have 3 sets of electrons around that plane. Remember that trigonal planar is right here? It's taken up by 1, 2, 3 pairs of lone pairs of electrons. So this is xenon F2, and this is going to be linear. Okay, this was T-shaped. This up here we said seesaw. Okay, questions? Let me see if we've got our let's go check the chem draw thing or the chem 3D thing and see if they give us one and they show us the lone pairs. They may not. I don't see one. Do you see one? Doesn't have to be the same one, but I don't see anything with 2 ligands on it. Okay, but linear is boring, right? Linear is linear. The important thing is when you draw the Lewis dot structure, and then think about the shape, is recognize those lone pairs go, they go into that trigonal plane around the molecule. And I'll tell you, if you're doing these structures, right, and you come up with something that you think is, so the way I could have done this differently is I could have drawn this with, I've got a xenon, I've got one of my fluorines going up top there like that, and I've got one of my fluorines in this bottom, this trigonal plane right here, and then I put in all my other electrons. What would this angle be if I did that? Hold that thought. Let's go up to our table here. So what if I had accidentally, I made a mistake, and I put my lone pairs there, 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 and I put my fluorine there and there? What would my angle be? $90 degrees, right? Okay. I'm worried that you guys, this is tough. I know this is tough. I want you to practice this a lot. So we've got, it would be this 90 degrees, and it would be bent, right? We call that bent when we have 2 atoms and there's an angle. So 2 atoms attached to the center atom. Okay, there never is a 90-degree bend. Okay, never. If you get a 90-degree bend, you've made a mistake somewhere. All right. Questions on 5 atom geometries or 5 thing geometries, electronic geometries? All right, let's go to 6 thing electronic geometries. The base structure here is octahedral. So you can think about a square down here, okay? And you can think about then something sticking up above the square plane and something below the square plane. And then here, we don't have this weird plane in the middle where we have 120-degree angles, and that's where our lone pairs are going to go. We're just going to stick our lone pairs so they're as far away from each other as possible, so the lone pairs aren't bumping into each other. And so you just stick them anywhere, really, for the first one, because however I rotate it doesn't matter. For the second one, I'm going to put them across from each other, and from the third one, put them across from each other as far as possible. Okay. So let's go and do some of these. So octahedral. So electronic geometries with 6 things. And let me be more specific on things. With 6 sets of bonds or lone pairs of electrons. When I say I'm saying 6 sets of bonds, a triple bond counts as one thing. A double bond counts as one thing. And a single bond obviously counts as one thing. Okay, the base shape is octahedral. All right, if you have played D&D, all right, it's the 8-sided die. So what's an example of an octahedral shape? Well, sulfur hexafluoride is an octahedral shape. All right, if I was to draw this just as a Lewis dot structure, I could do it like so. All right, the octahedral shape is like a square bipyramid, but we call it octahedral. And so an example of that is, this has got to be one. Yes. So here, this isn't our sulfur hexafluoride, it's a phosphorus hexafluoride. Okay, but it's this shape. And you see if I tip it or turn it, you know, we see it, you may see a plane right here, but there's also a plane right there, and there's a plane, you can draw planes that are the same, those square planes that are the same throughout or wherever. So they're all equivalent positions. All right, let's go ahead and do square bipyramidal. Or not, so square pyramidal, I should say. So if we have B, so this is octahedral. And then if I take BRF5, let me do a proper lowercase r there. BRF5, that's going to be BR in the center because what? Why? It's electronegativity. It is more or less electronegative. Which? Less electronegative. It wants electrons less, and so it's more willing to share than fluorine, which is pretty much nothing shares worse than fluorine. I guess except the noble gases. They don't share at all. Okay? And we'd have a lone pair down here. All right, so we call that square pyramidal. And that's like a proper Egyptian pyramid, okay? Maybe you're probably not seeing the shape there like I am. Let's go ahead and look at one. I'm trying to find one. I need 5 things, right? It's not that. All right, let's try this. BRF5. BRF5. Vesper shape. And we'll do images. All right. So if we look at this structure, I can't tilt this one around. Oh, but we're going to get an insurance ad. You should get your insurance from Liberty Mutual. Support YouTube. Anyway, you see this? You see how here is it obvious? It's a square pyramid. Like if I filled it in, it would be a proper Egyptian pyramid. Okay. Okay. So that's square pyramidal, and then we can have square planar. All right, so for square planar, we have 2 sets of electrons on it. A good example of that would be xenon F4. So xenon tetrafluoride. And so that's going to have a lone pair above and a lone pair below, and then it's going to have a plane that I have fluorines in, like so. Okay. And if we look, this one we do have, I think, over here. Here it is. So this is talking about dipoles, but here we have, this is xenon tetrafluoride. You can see it's a square plane, right? And there's a lone pair up here and a lone pair down here. Questions on that? Okay. Then there are a couple more on this table, but when I was writing my note, I see from my notes last night, when I was writing down from your book, we didn't go beyond square planar, so we won't bother to go beyond square planar here. When I think back to college, I don't remember going beyond square planar either. So let's not worry about these. They exist, okay, but we're not going to worry about these for now. And that's it for these shapes, okay? You're going to want to practice that a bunch. Lots of good problems in the back of the book. I will give you whatever activities we've got that allow you to do them and get all of your points, but they're generally not as good as the problems in the back of the book, okay? Questions? Okay. All right, then I want to talk about one other thing that's involved in bonding here, and then we might cycle back and do some practice problems, but I don't know if we'll have time for that. So we can talk about molecular or actually I want to get the term right here. Hybridized orbitals. All right, and hybridizing these orbitals is important, really important in organic chemistry, and it's going to show up in the lab you do after you get back from break. All right, so I'm going to talk to you about it now. I am not going to put it on the test, but do write it down so when you go to lab you kind of know what it is or think about it. All right, so when we think about some of these shapes, right, we've got these orbitals that stick out. You imagine, let's just look at our P's. All right, that gets more complicated, but let's look at our p orbitals. We've got our p orbitals. We've got one that goes up and down. We've got one that goes out this way, right? And we've got one that comes out towards us. We're going to put all our p orbitals up and down, left to right, and we one that comes out towards us and one that goes back. All right, but when I go ahead and make a methane molecule, if I think about methane, I've got a carbon, I'll have a hydrogen that'll stick up this direction, I'll have two hydrogens that kind of come out at us, it's a tetrahedron, right? And I'll have one that goes back. How the hell do I get that shape from those orbitals? Okay, you'd imagine I've got some electrons up here, so wouldn't I stick a hydrogen up here? But then how do I get a tetrahedron out of that? And so what the theory, the thought is on this is that if you mix orbitals, if I take my s orbital, right, which is this big circle that I'm not drawing here, but our s orbital could be this as well. Okay, got my s orbital. If I take that s orbital and I mix it mathematically with some p orbitals, then I can get hybridized orbitals that give me that shape. All right, so what that is if I take an s orbital plus a p orbital plus a p orbital plus a p orbital, right? I'm going to get what we call, I can mix to get, there's 4 orbitals going in, so I can get 4 sp3 orbitals, which I understand is confusing and really vague. Okay, but it gets used all the time in organic chemistry. And so we call that hybridization. And so we would say that if we do this, that the carbon is sp3 hybridized. All right, and what these orbitals would look like then, I'm not going to try to do the art here. I'm going to hope to not click on another ad. So hybridized orbitals. And we just want a picture. Okay, so here we've got an example of the hybridized orbitals. Okay, so this is what happens with that. So if we do this hybridization, we end up with 4 sp3 orbitals and they look like this. Does that make sense? And you see how that fits the shape of our CH4 right there? All right, so you can mix, I want you to know and have seen that you can mix these sp3 orbitals. Here's a actually better diagram. It doesn't look like that's a YouTube video, does it? So what they're doing over here is they're mixing these orbitals, and they get, you see how you get these orbitals that go 3 different directions, and when you put them together, you end up with something that looks like this. So we can make that CH3 that's tetrahedral. It's how we get our tetrahedral. And that's kind of all you need to know. When you go to organic chemistry, you'll talk more about it, and you'll talk about what's the hybridization on the carbon, and that's actually very useful for predicting what the shapes of molecules are. If instead of mixing 3 P's with an S, if instead I mix 2 P's with an S and P plus an S and a P, I can get same number, you put some number of orbitals in. If I put 3 orbitals in, I get 3 orbitals out. I would get 3 sp2 orbitals. All right. And what that makes is a trigonal planar arrangement. So I'm going to get something that looks like this to the best of my ability to draw it. Okay, so let's do sp2 orbitals. All right, and do you see this? So they're kind of showing that if I take one of these and 2 of my P, one of my S's and 2 of my P's, I get these sp2 orbitals, and so that gives me a trigonal planar arrangement. And you can see there's all sorts of other complicated things that you'll learn about in organic chemistry. Okay, and then finally, what I can do is I can mix one S with one P. So I can do an S and a P, and I can get two sp orbitals. And what that's going to give me is my linear arrangement. Okay, I get my actual sp orbitals look like this. And you put the two together and you get the linear set of orbitals. You can make linear molecules in organic chemistry with that. Questions? Okay, I'm going to introduce one more concept with this. All right, that we're going to use. So let's take this one. Okay, how many p orbitals do I have total? I have 3. I have 2 there, but how many do I have total? I have 3, but I only used 2, right? So what that means, that leaves me a p orbital, brought in yellow, that sticks up like this and sticks down like that. Okay, and so in organic chemistry, when you make double bonds, they're showing an example of it right here. Actually, that's a triple bond. Let me see if I got one better. Perfect. This is the one I want. All right. So here, what I've got is I have these sp2 orbitals here. sp2 and sp2 are making a bond here, and then I can get a bond with my 2p orbitals. This is a double bond. When we talk about a double bond, we show those double bonds. In organic chemistry, it's sp2 plus the extra p is causing that overlap. And I think that also shows up in your lab after break. So you can write that down in your lab after break, or most importantly, when your lab instructor says, do they cover this in class? They're going to cover it again because it's been to break. You go, yes. All right, other than that, please practice those shapes. This hybridization will not be on the test, okay? Focus on the shapes and the Lewis dot structures and the formal charges and the other stuff we did before that since the last test.